much for the nice introduction, and also thank you very much to you and Suresh and for the invitation here. It's my pleasure and honor to give this presentation here, which is, like you've seen, coming back a little bit to earlier in relations to earlier presentation, and it's a talk about networks of networks, because what I'd like to do is to talk about relations and interactions between natural rivers and especially river networks and urban systems, including wastewater treatment plants and stormwater drainage systems that you have heard a lot about these today. I will take an ecological or a receiving water perspective and will ask from the river's perspective what are relevant connections probably, and what does this mean with regard to ecological properties, ecological functions, and not to forget management implications. I will take this figure to talk about rationales. Why are we doing and why are we looking on these interlinkages, on these networks of networks from a kind of normative perspective? Why do we limit urban emissions, and why and which kinds of measures do we take if we want to understand the extent and the relevance of anthropogenic impact versus natural dynamics on the status and functions of aquatic ecosystems? And let me take the EU legislation as an example, which is a framework that we have that tries to set up a gradient. This is a gradient of pollution, you can say, or of ecological alteration, which typically, like many others in the United States and Australia or other countries of the world, is defining some classes, so some normative sites, which basically rank a kind of deviation from a situation of a given aquatic ecosystem, which is has no or a minimum anthropogenic impact, and typically, in Europe, we want to achieve a state in order to sustain biodiversity, but also ecosystem services, other things, in a condition which has only slight deviations from this, what we understand and could parameterize as a natural system. There are important implications. So this is typically the target. So it's not the pristine world, but it's a world with some anthropogenic forcings. And on top of that, typically we don't want the receiving waters to further deteriorate. So it's also important to understand how, in a future perspective, under changing anthropogenic forcings, and we have seen many historical examples, but we have also seen examples about climate change, future land use changes, increasing of agriculture, all these things, including urban developments. All these should develop in a way that a given status that we have at the moment may not change significantly in the future. And on the other hand, if we are in a state today, which is a state which is less than a good one, it calls for restoration and therefore for targeted measures to change those environmental conditions in our receiving waters that then are changed in a way that a better ecological functioning can be achieved. So this is a normative background between and behind also the relations that I'm going to talk about. Why is this an issue? This map shows you for Germany, and the figures are not very different for Europe. This shows you the ecological status of today's river networks in Germany, and you see that here a yellow, red, and orange color dominates with regard to ecological status, why it is a little bit better for the chemical status. It shows you that still a majority of river systems that we have obviously are ecologically affected, instead of having developed networks of urban water management, but also in other sectors. I will go about the reasons for that in detail. So let's talk about a river's perspective and how what can we say about water and metafluxes from urban catchments in a given environment where we have a landscape like this one with some probably more pristine areas here, some agricultural areas here, and then the urban environments there. If we look on modern lifestyles, it's very clear, like we have already heard, we have a given consumption patterns with regard to drinking water. Sometimes it has been historically higher, as we learned today, when compared of today, but it may also increase in the future. Then we have specific per capita emissions with regard to nutrients. We have a chemical lifestyle using a large cocktail of chemicals that we release every day to the wastewater. And of course, there's a certain there's a certain amount of sealed surface per inhabitant that we have changed with regard to the surface characteristics given average European figures. A second aspect is we have multiple entry points of these pollutions in a river network. Typically, our nowadays design criteria work in a way that they are only related to the point of the entry, but they don't care about interlinkages, including overlaying effects and things like this. So from a river's perspective, we have to be aware that we have multiple entry points of these pollutions in a river network. And so, therefore, the river network play a role. So the challenge is, what I think, could be a question, can we manage urban sewage systems, which mean both the sewer networks and the wastewater treatment plants behave in a way that there would be no urban systems or sewage systems, or they have only an impact which is so minimal that the resilience of the ecological system is not affected adversely. So this is a core question, and if this could be answered after these 3 weeks, I would be happy. But I come back to that. So let's look at a little bit more detail about networks, and from a receiving water perspective again. We have seen other examples. This is showing for Germany a map which is, I think, very exciting from a hydrological perspective, because it shows the water balance, the natural water balance in relation to the water consumption, and you see different colors here, and the more yellow and more orange the areas get, the larger is the discrepancy between the water which is there hydraulically and when compared to those which is used. And you see there are larger spots, entire catchments obviously, where more water is used in these areas than it is actually generated there. And you see larger red connections here. These are the long distance water supplies that we have in Germany, from reservoirs into big cities and so on. So these are long distance water supplies, and you can imagine that these also regionally affect the hydrology of the receiving water systems, because they end up as dry weather flow via the wastewater treatment plants in the receiving waters. So there is a hydrological effect on that. I will go into more detail. So this is one aspect. So if we look on the dimensions of the networks, these again are the figures for Germany. We have some 10,000 wastewater treatment plants. We have some 450 kilometers of sewer network, which is more than 30 times the circumference of Earth. So it's really a significant amount of pipes which are underground. And if we look on the wastewater which is treated, this amounts to one of the larger alpine lakes that we have, Lake Chiemsee. Some of you might know that it's 5 times this volume of a really big, large alpine lakes, which is equivalent to the amount of wastewater that we are treating each year, with some removal efficiency, but which is not complete. So there is some residual pollution. The message is these are large volumes of water, and the removal efficiency, of course, is not complete. To put this in perspective with the river networks and the river ecologies, we have a river network in Germany which is about, in length, about 27,000 square kilometers in length, with catchment sizes above these 10 square kilometers. So larger, big river network. The different colors show you the different ecological types we have. So these are river systems which, because of their hydrological and morphological properties, own specific ecological communities, like fish communities, macroinvertebrate communities, and so on, Descriptions are available, I don't go into details, but there you see with these river networks there's a certain ecological characteristic which is associated with these networks. Some relations: if we have the 540,000 kilometers of sewers, we have 127,000 of rivers, which is a ratio of 4.4 to 1, so we have more sewers than rivers, and we have roads somewhere in between. So these are the relations between the networks in terms of general dimensions that we have, and I think it's a good argument to look on this closer. Let's look upon the design criteria. Peter Cripps and colleagues have already talked about it. So we have well-developed infrastructures at the moment. As I said, 10,000 wastewater treatment plants are in stage and so on, so we will not see these significant developments that we have in the future, but we very much have to cope with the rehabilitation. There are certain general characteristics which are, for example, minimum dilution capacities that a storm overflow has to have, a minimum storage capacity which amounts to 2.2 to 2.5 millimeters of rainfall. Then we have a certain wastewater load in terms of COD or other parameters which is entering the rivers on an annual basis, and this is linked with a certain number of overflow events, which amounts in our cases to some 40 to 50 events per year. And we have seen of some of the characteristics of single events from Peter, and we have the continuous emissions from the wastewater treatment plants. That means we have a more or less time invariant emission there, and we have a highly stochastic one here. And these are interlinked because of the flows that limit the functionality, or that they are limited to sustain the functionality of the wastewater treatment plants. So interconnected networks also between the wastewater treatment plant and the stormwaters. I'm not familiar with this. Whoops, no, it's the complete wrong direction. Get back. And there's another important aspect, and this is the size of the wastewater treatment plants. And you see we have different size classes. So we have 5 in Germany, and they have different technical capacities, but also limiting technical designs with regard to the pollution that they are allowed to discharge to the environment. So it's also a factor of the size and the character of the given sewer system in a network context. So what is the characteristics that we have to talk about from the receiving water impact? So if you have a separate system, which are typically more typical in other countries like Australia, for example, but also in the United States, not in this complete ideal form, very, very common in Germany, maybe in some northern parts. So there, the important point is the pressure is characteristic in its intermittent character, so it's a mixture of different flow components which end up here in the river, surface flow and then transported, and this creates peak flows, increased frequencies of critical shear stress, sediment and bed load transport. And if we look about combined sewer systems that we have heard about, where the stormwater is mixing with the dry weather flow, we have the same, we have a different hydrological character, and you will see it in a minute, and we have a much more complex, let me say, chemical cocktail which is there, and therefore the substances we have to talk about. Let's talk about water pathways and balances. So if we look on the basic differences between the hydrological properties if we have a rain event, then if we have, let me say, a more natural system, the typical pathway is that under these conditions the evaporation and transpiration is the dominating pathway, a certain amount is infiltrating and a certain amount becomes a surface runoff and then also enters directly up into the river. It's completely different when we look about on sealed surfaces. Here the runoff component is much higher because of the physical characteristics of the surfaces. We typically have a very low infiltration and some evapotranspiration which is left. Coming back to my initial phase, if you look at this on a scale, we see this map for Germany giving the precipitation and evapotranspiration, so two of these elements of the equation I have shown you. You see a large heterogeneity in given catchment, which means that it is obviously a wise decision to look not on general figures for one region, but to look very much about the relevant hydrological characteristic, including their variability in a given setting. And it's not the same if you look on the different elements of the equation. So the heterogeneity when it comes here to precipitation and evapotranspiration is different with these two components. So then it is very clear if we look at from a very simple balance equation, it could be a meaningful exercise to look, if we have an urban area, how the flow separation is working. And this is quite simple if we look on a very general water balance equation in an equilibrium, and we can even do it in a dimensionless way and maybe derive some separation factors that characterize these different flow pathways from a hydrological perspective. The interesting point is, if we look at these, and this is an example showing 3 different types of urban settlements, you see that these different components, they differ between these characters. I don't go into details, but the interesting part is that these are these dashed lines here. These would be the situation if there would be no urban areas. So you can see both elements. You can superimpose, so if you have a high retention, for example, but you can also affect a regional hydrological system significantly if you, for example, have a 90% sealed surface and so on. So this would allow to make this linkage. I was asking at the beginning, how much is our potential to mitigate our hydrological alteration towards somehow more natural conditions. So this is one thing we can do. And the second thing is, when it comes to runoff generation and receiving waters, okay, we have heard about these characteristics that network architecture counts, and this is very clear if you look on 2 catchments receiving the same precipitation and runoff, they create completely different hydrographs. Why is this important? Because at a given hydromorphology, a peak flow like this one would create a completely different shear stress as a result, as a flow force, which is then acting on the ground of the surface water when compared to this catchment. And this has been measured nicely from Swiss colleagues, showing the typical pattern, what is happening with the flows in a quite simple catchment. And you see here a flow graph. These are a few hours. Here are rain events. This is an average event happening 30 times a year. And this is a flow which is caused by the urban area, and this is a natural flow from the upstream catchment. So you see under a given rain event, there's a very smooth flow reaction because of the retention process in the natural catchment, while the urban one acts fast. The important point is it exceeds this Q crit, which is the critical flow causing bed load transport here in the system. So in a natural system, there would be no one, and from the urban system, there is one even at low events. While if you take a larger event, 1 time per year, with terms to bed load transport, these act the same. They exceed the critical shear stress, and volume is higher, but the disturbance regime would be the same. So this is a basic characteristic that we have. So this type of having and looking both on the hydrological reaction, but then on the hydraulic reaction, is the important one from the ecological perspective. Now I've talked about chemicals. It is very clear that chemicals are another thing. We have seen nicely from Peter that some behave like ideal traces, conservative ones. Other ones, like suspended solids, are transported in a different way. Now we have a really huge cocktail. So this is a chromatogram of wastewater, typically for Germany. What is in there are some compounds. So there are 300-500 compounds that are detectable in a typical wastewater that is entering and receiving water. The big question is what are the characters of these chemicals? What are their adverse functions maybe they have, or impacts they have in the receiving water, and do we have surrogates to characterize this chemical pollution, because it's very clear we cannot either even monitor, but definitely not model all these 3,500 components. So it's a good idea to reduce and to look on surrogates that can be used, which are much more functional surrogates of these large cocktails that we have. One point is very clear. If we look at these surrogates, then, and this is from our observatory at UFZ, Uppsala. I do not learn it. This is longitudinal profile of a river, some 40 kilometers in length, having 2 wastewater treatment plants, one here, one there. And these are some of the components, and you see that at base flow, so if you have a constant flow, then you really get profile that perfectly fit with and could be assessed with mixing models that show the dominance for those effluents or for those contaminations who are typically wastewater based. There are some, like these artificial sweeteners, for example, some perfect tracers. There's borate, for example. It's also a perfect tracer for chemical pollution, so these can be taken as such surrogates. But base flow is only one hydrological moment in time. So we have the varying discharges, and then we have a point source dominated river. We have and we have other models for those who are much more dominated by agriculture and groundwaters. Then we have this type of relationships, and therefore we can statistically work with such kind of relations to understand and to analyze the impact of the wastewaters. From the ecological point, if we talk about this phosphorus, the range of the favorable conditions is not constant over the year, over the whole hydrograph, but it's especially relevant in the time. For example, the algae, they only can grow if there's light, if the temperature is high enough. So it are only partial series of the flow concentration curves where this is really ecologically active or biologically active, and this corresponds, and this may exceed limiting concentrations, but if we think about flows and erosion and the flow control of discharge by bedload transport or by high shear stretch, which detach these algae which they grow, there's a co-limitation of flow and the nutrients. So in this sense, maybe there we can work with these exceedances and also can analyze the co-control of nutrients and hydrological conditions in a way. So this is very clear if we look at one point, like also Peter did, but what is very clear if you have networks in mind, and we have seen the examples how urban settlements are scattered around and across networks. So the question is there a role, or is it only a matter of loadings and concentrations which are somewhere in the system, probably at the end point, or do the distributions of the networks count? In other words, is there a network perspective that could put us a step beyond compared to what we are doing today, limiting single effluents? And I want to expand on this, taking a river network again from Germany, a typical one as an example. We have other examples. Katja has one on this poster yesterday, where we have river networks like this one, with some characteristics even with regard to stream orders and stream densities. And what we typically see in this catchment is we have some 100 wastewater treatment plants, and they have a certain size distribution, which is very characteristic. And you see, here is a number of population equivalents, which is connected to the given wastewater treatment plants. So these are very small ones, only less than 1,000 people are connected. These are medium-sized and they increase, and these are the large tertiary treatment plants with high technology with more than 100,000 population equivalents connected. And you see that there's a kind of distribution. So we have a large number of small ones and then a decreasing one and end up with 2 or 3 large wastewater treatment plants in this catchment. This is nice because from a load perspective, this is meaningful because it's very clear if you look how many people are connected and therefore how much wastewater load is connected, then these only 2 or 3 wastewater treatment plants, big ones, they treat the largest amount of wastewater and therefore also create the highest load of the entire catchment, while obviously, or it seems to be that the smaller ones do not count very much. This is nice, and you can say, well, what are you talking about? If I look to the entry points of these discharges, then it's a little bit different. What you see here is the mean annual base flow at those points where these single stormwater overflows and the wastewater effluents enter the river. And you see that a large majority of the entry points is below 10 liters per second and square kilometer, which means this equals 5 square kilometers. These are the very small streams and creeks that have to cope with these emissions. So the highest specific loads in terms from an ecological point of view could be observed in the small streams, not in the biggest ones. These are those points where we have at the moment the lowest emission standards. So the permitted wastewater discharge is highest. If we make a very rough assessment and want to look at a characteristic impact length, so imagine there's an entry point, there's a pipe ending up in a river, some either stormwater or wastewater treatment is entering the receiving water, then there's a certain transport and a certain natural turnover unless you get back to some closed position, something which is also termed as being self-purification. And if we do this for the network, then the figure is reverse when compared to the loads. We are talking about concentrations and we are talking about characteristic impact lengths. So the majority of the river network I have talked about, so this river network, so it's 80%, these are affected by these small treatment plants. So the small treatment plants control the pollution in a network perspective, while the big ones control the loads. And therefore we have a kind of optimization problem probably, which to my knowledge is not systematically analyzed so far. And this was a big motivation to enter this workshop and to think about these questions. And then I come to Peter. I use this figure. Peter already announced it. So this nice and very exciting reverse behavior of the return periods, talking about peak concentrations and the rain intensity. So it's a small and medium-sized, not the big ones, like you would first assume, the big stormwaters, but the medium-sized and small events which count. And this is true. No, it's not true, but we have evidence also, and I will show it from an example. This is a synthetic example, which also could be an example that can be used during this workshop. By the way, this is a German design network which is used as an example to plan and to operate combined sewer systems, which has some characteristics in terms of a medium-sized city with some average precipitation, average sealed surfaces. And this is done what the emission standards do. If we do this, they have to create a certain storage volume to control some kind of emissions of the combined sewers, which ends up in some 1,500 cubic meters of artificial storage that have to be created. What we did is we connected a river network. And we added on a wastewater treatment plant with some characteristics, A river, B creek, and C stream. This is a surrogate also for stream orders. Let's say this is the first order stream or creek, river, second order, third order. And this is what we typically have in networks, in urban networks, we have some of these overflow devices that end up in small rivers, other ones, including the wastewater treatment plant, in the bigger parts, and other ones there. What does this mean if we look locally on the hydrological effects? So if you make a water balance for a rainfall with a return period of 1 year, you see, and you only have to look on these factors of X, which are an exceedance of the potential natural flow that we would have with this return period. So it's simply an addition to the natural flow dynamics, and you can see in some areas it's very, very low, and at this discharge point, for example. Another one where we have a large stormwater retention, the frequency is even only one event per 2 years, so it's much lower than this one. Ecologically, maybe not so important. And here you see the really big differences, 100%, 20% here. So it's a factor of 5 on a local scale if we look on the hydrological effects. But this can be used to assess this type of behavior. When it comes to water quality, here's a graph that's showing again on a stationary balance. So here's a specific runoff between very low rain and runoff intensities until higher ones. This is also a return period between close to 0 and once per year. And that is the resulting, in this case, oxygen condition in the receiving water at this entry point. And this is a critical threshold that we have as a receiving water standard in Germany. You see there's nothing happened about oxygen. Why could this be the case? It's very easy. The physical reaeration of these rivers is so high that there is no effect from the loadings that we have. It's completely different when we talk about ammonia or non-ionized ammonia. And there are these visible 3 spots that show the same behavior that Peter has shown in this graph, where we have the small and medium-sized event that create the exceedances of this threshold. And this is a very interesting part because this tells us, probably I should solve the next one is again. So if we have this, what can we do about it? We can then, and probably should include, interventions. So typically if such an exceedance of thresholds is observed, one starts to think about what can we do about it in either improving the oxygen or lowering this oxygen signal here, or what to do about these peak concentrations that we want to have below these thresholds. And then it's very important, I think, that the system itself and its optimization comes into the game, because we can do probably 2 things. There's a wastewater treatment plant that has a flow restriction of 2 times the dry weather flow, but typically has exceeding capacities so that we could increase the dry weather flow to the wastewater treatment plant. And in this case, if we only do it slightly, we solve this problem. So it's an interconnection between the stormwater part, the dynamic part, and the constant part. And if we, for example, would build here a traditional storage tank, nothing would happen with these peak concentrations. But if we use this as a constructed soil filter, as constructed vector end, then we can handle this system. So it can also be used in a way that we can talk about a much wider variety of measures from this network and this interconnection perspective, which I think is very challenging and also, I think, innovative. So let me talk about what we could do about this on the workshop, and then these are my last probably 1 or 2 slides. What I think is really exciting is to talk about network of networks. In this case, what do we do in a catchment perspective with these systems? So I think we have data here, we have concepts here. We then could talk about stochastics and frequency distributions of pollution characteristics, polluted glass probably. Katja has shown some of these empirical data in her poster. And we have also some data which are linked with treatment strategies, wastewater treatment strategies that have been implemented at catchment scales. And these 4 graphs show the evolution, in this case, of phosphorus loadings from a heavy pollution phase to a rehabilitated phase. And this for different types of the catchment, so a difference between upstream and more downstream, lower polluted or areas with lower urban wastewater load and those with higher ones. So there is some also empirical background that can be used for testing the real world's evidence. And then I think it's this interaction, which is interesting. It's these different urban sources, the stochastic and the invariant part, I think is also conceptually a nice point. Then we can talk about different goal functions. I would propose to work on hydrology, hydraulics, and select some water quality components that we can handle easily. I think there are some. And then we could work about and towards frequency distributions that can be used as a nice measure to understand the interaction, but also, relevant effects, relevant parameters, systems behavior, and things like this. And we also, and this is what I'd like to see, what is the if we have a given pattern of urban settlements in a river, what is the minimum of the river length under given thresholds? We can talk about different thresholds, but we also can talk about the positions. And I would see, I've never seen an example that has tested this. And if this could be a way forward, I would be very happy. And this would be really exciting. And this leads me then to Zurich. This is something we have discussed because this has to do with trajectories. So if we talk about a natural state or a least impact state, so this is a gradient of human impact. This can be also parameterized for urban areas, and we have one which are less polluted, other ones more heavily polluted. Then it's very clear that under examples we have shown, we have seen, or we can assess how a degradation happens, but then if we take technical measures or management measures, we can analyze how these systems then in which directions they turn. And this leads to the questions of trajectories, which I think would also be very, very innovative and challenging to look at, and probably we also could work on the empirical evidence for that. And this is my end. So I come back to my question, can we manage urban sewage systems with river networks behave in a way if the urban visions were not there? If you could solve it, this would be something. Thank you very much.